In this video we are going to speak about minimum and maximum values of bounded functions. Especially we are going to mention how derivatives are applied to solve extremum problems. To begin with, we have one function here which is given in this graph, and there are certain values for which we can see that they represent some extremal values. Before we analyze this graph in more details, we need some concepts, and those are the concept of relative minimum. We say that f of x has a relative or local minimum at x equals c if f of x is greater than f of c on some interval containing c. So this is on some interval around c. It has absolute minimum if f of x is greater than or equal f of c for all x in the domain. So the difference here that there is some interval around c, and here that this is for all x in the domain. So this is on some interval, this is for all x in the domain. Furthermore, we have a relative maximum, that is just that f of x is less than or equal f of c, again on some interval around c. An absolute maximum if f of x is less than f of c for all x of the domain. Okay, so relative minimum or relative maximum, or we also call them local minimum and local. Okay, this is the same, and this here. So relative or local, and absolute we also call it global, and here also global. Okay, so now we can go back to this graph. Notice that minimum and maximum are the values from the domain. So minimum and maximum, min and max, are contained in the domain. So the function must be defined there. From this graph here, also we want to, before I go now back to this graph, I just want to comment on here what we have. We have unbounded and positive. So if the function is unbounded and positive, then it cannot have maximum. And if the function is unbounded and negative, then obviously it cannot have minimum. You can always think about the function. The easiest one of the easiest function in this context is the function x cubed. So x cubed doesn't have maximum, even the function f of x equals x. So the domain is whole R, and the function is not bounded, and hence doesn't have neither a minimum nor maximum. There are different ways how you can conclude that, but I'm just mentioning that so you can remind yourself on that intuitive, obvious fact. Now let us go back to this graph. We can see that A here, looking from the graph, if you put like a strip here, you can see that the all values are within this blue strip that I just introduced. And you can also see that D is global max, whereas A is global minimum. Why? Because on the whole domain those two values are dominating. If you take an interval large enough that contains B, then you can see that on that part of the graph, let's say this that I'm going to mark as blue, that B is local maximum because it is greater than all other values from that interval. Similarly, you can conclude that C, taking any suitable interval, you can see that C is local minimum. Okay, this is local maximum. And also taking a suitable interval around E, you can see that E is also local minimum. So that's the value there. I will mark those values as with the blue color, and it's now clear what they represent and what is their nature. Of course, we haven't mentioned here the coordinates of the points A, B, C, D, E, but we just want to know how to identify them from the graph. You can also notice some knowledge here of graphs and interpretation of differentiation and derivatives. You can see that f is not differentiable at x equals b. And you can maybe pause the video and try to explain to understand why is f, if this is f of x, so this is the graph, why is it not differentiable at b? Okay, so we have introduced a couple of concepts, and now we want to see what are critical values, because with these critical values we will see how derivatives and extrema are related. All critical values of the function f are such values where f prime, or the first derivative at that value, is 0, or the first derivative doesn't exist. So those are called critical values. So critical value is such a value where the first derivative is 0 or first derivative doesn't exist. That means doesn't exist as a real number. Okay, so those are critical values. Next, speaking about extrema, there is a famous theorem from the theory of continuous functions which is called theorem on continuous on the minimum and maximum of continuous function, and that theorem says the following. So it says if f is continuous on the closed interval AB, that's essential here, then there are CD from the closed interval AB, so it can be AB also, such that and C is less than or equal D. So f of C is global minimum, f of D is global maximum. So that is the theorem on continuous functions on the closed intervals. So that means that the function which is continuous on the closed interval attains its minimum and maximum. So another way is this to say is continuous function on closed interval attains its minimum and maximum. Okay. Now, the question here also that I want to highlight, that's the next question, is what minimum and maximum have to do with derivatives? Because we are speaking about derivatives. And the answer gives the famous Fermat's theorem, especially when it is we speak about relative extrema, so local. So I will just write here local extrema. Okay, and Fermat's theorem says if f of x has a relative extrema at x equals a, and f prime of a is real number, then x equals a is a critical point of f of x. For that critical point, x equals a holds f prime of a equals 0. In other words, so let's say, so that's the Fermat's theorem. Other words, so I will just, in other words, candidates for relative extrema are solutions of the here it's meant relative extrema of f of x, of course, so we speak about the function, are the solutions of the equation f prime of x, or f prime of c, if you want. So f prime of a, so f prime of a equals 0. And of course we assume that f prime of a is a real number. So we obtain that this characterization. Now there is an opposite, so the opposite is not true. So if, this is important, so if f prime of a equals 0, then a doesn't need to be a relative extremum. Okay. Here is an example. This is a standard example for this one. So if you have f of x equals x cubed, okay, and f prime of x equals 3x squared. So obviously x equals 0 is a critical point. Why? Because f prime of 0 is 3 0 squared, which is 0. But 0 is not relative extremum. Why? You can pause the video and think about this. Actually, this comes from one fact that we have mentioned at the beginning, and I even mentioned this function. This function, it comes from the nature of the function. This function is not bounded, basically. And it's continuous, so plus continuous. So it cannot have minimum or maximum or relative. It can have relative extrema, but this specifically, this function cannot. And if you recall the graph of the function, that's the function that goes like this. Okay, so this is x cubed, and you can see f prime of 0 is 0, but here it's not. It is a critical point, but not extreme. I will just come back to again what I have mentioned about so being bounded or unbounded, because we have to be very precise when we use mathematical language. Now, of course, the function might be unbounded, so it can be unbounded and can have like relative or local minimum. I will just put this example, and then you can think about unbounded and local maximum and so on. So you can modify actually the function x cubed. So if you have the function, and this is the typical case with polynomial functions, which also you can think about. So it can happen even if they are continuous. So it can happen something like this, and then the function goes up. So obviously the function has two local, so this is local maximum, this is local maximum, this here is local minimum, but there are no global minima or maxima. Why? Because the function is, as you can see, unbounded. And it is unbounded in positive, unbounded in negative, so no global extrema. This is what I meant at the beginning, speaking about unbounded. The function can also have, even doesn't need to be continuous, but it can still have extrema. So you can think about that when you come back to this theorem of continuous function. So the function still can have minimum and maximum, but it doesn't need to be continuous on the closed interval. Okay, so this is the first part, so introduction to extrema, of the nature of extrema, and the most important part here is the Fermat's theorem here, that is most of the time used in differential calculus, and this is actually the answer what minimum and maximum or extrema in general have to do with derivatives. In next videos we will then see concrete examples how to use that theorem and other theorems to identify global extrema and global and local extrema. Thank you for watching.